על IL Tech Talks כבר דיברנו ועל היכרות כבר עשינו. גיל, תגידי מתי אפשר להתחיל. אפשר. Okay, so our lecture today is about, the title of the lecture is From a Kafkaesque Story to the Promised Land. Kafkaesque story and the Promised Land are both terms that came from Jewish legacy. Kafkaesque is about from Kafka, a writer, Jewish writer, in the beginning of the 20th century. And the term Kafkaesque story talks about something that is hopeless, without any way out, a situation when a person feels he's caught, trapped in some situation that he cannot get out. It's because of the stories that he wrote, if anyone read his stories. And the Promised Land is a term that came from the Bible, talking about when the people of Israel came to the land of Canaan. They knew it's their promised land, but they also knew that they need to conquer this land. They didn't just got it. It was their land by law, but it took them many years, hundreds of years, to take over all of the land. So in this lecture, I want to explain how we move from a psychological situation where we feel that it's a hopeless situation, the data platform, to a place where we can see a vision of where we're heading. We might not be there yet. We might feel that there's still a long way, but we know where we're heading, and we're working to conquer it on the way there. So what are the challenges of data platform for LivePerson and for any other company that deals with big data? I have some references in the end to some papers, but I will not mention them right now. We can look in the end where I took them. So we have quite many challenges. First of all, we need a very high throughput because at least in LivePerson, and maybe I'll just mention what LivePerson does. LivePerson is a service that monitor the data from our customers. Our customers are internet sites, and we monitor what they do, and then we help the customers engage with their visitors in the sites. So we actually monitor many sites, many pages, and there's a lot of data that is streaming to our real-time servers, and we need all this data to be collected, and we need a very high throughput. And not only a very high throughput, but we need to know that we can grow, and grow horizontally, meaning that we see that the traffic grows. We should have a very simple way to scale to bigger and bigger without, and it should be horizontal, meaning that we know that that if the traffic is twice as it was before, then we can have twice the number of machines. That's a horizontal scale. Not only that, we need this service to be very highly available. Because if the service fails, we don't get the data to pass. We need the data immediately to be available. The whole system should be highly available. Not only that, we don't want to have any data loss. We want all the data with a high availability, with the horizontal scale, not to get lost, all the data. And not only that, we also want to satisfy our real-time demands, provide real-time dashboards that we can see exactly what happens now, what our customers want to see at this point, who are our visitors, what are they doing, are they engaged in chats, whatever, real-time dashboards. In addition to all the above, it's very important to us to enforce the data structure to some schema. Why? Because every time the data model changes all the time, there are new releases, changes. We want some way to manage this. And we have customers that are enterprise customers, which has a lot of data, and they have very strict demands for reporting, for data uploads. We need to provide all these services for them. And we want all the data that is stored in our system to have some kind of single source of truth, because we had in the past different systems, and each system managed different types of, or different parts of the data, and then when we compare the system, they are not the same. Different systems calculated the data differently and provided different outputs. So this is the list of the challenges that we as a data platform LivePerson face. It seems like a big list. It's frightening. How can we address all these? But I'm going to show you today that we actually address most of these needs. And if not now, we're heading there. As I said, going to the promised land. We have most solution for most of these topics. Another thing that I want to mention here before I start to drill down is what are the SLAs, the service level agreement, that we as a data platform provide to our customers. Customers are the users of the system. We provide a data platform. They are users. The users are here I have two different users. One are offline customer, which generally are the people that create reports. They run reports. They want to know what is the data that was collected the last day, the last month, last week, the last year. These are offline data customers. And we have real-time customers. These are maybe the same users, but they have different purpose. They want to know what is happening now, as fast as possible for all the data that we aggregate. So we provide two different SLAs for these two. For the offline customers that are doing reports on offline data, actually data that was collected into Hadoop, we suggest an SLA that tells them, okay, 90, and the numbers might not be accurate, it's just for example. But we can say that in the first half an hour, you will be able to get most of the data. But after 4 hours, you will get 99.999% of the data. Why it's only 5 nines and not 100%? Because there's never 100%. We cannot guarantee 100% because that will be lying. Always something happen. But when we say this number, it's a very high number, and it should be accurate that almost all of the data, eventually after 4 hours, will be available for the offline consumers' reports. On the other hand, the real-time users, they need the data very fast. So we say 98% of the data will be within 500 milliseconds, less than a second. But if it took to the data to arrive more than 2 seconds, then it's not interesting anymore. Because as a real-time dashboard, I don't want to see data for something that happened 2 minutes ago. It's not relevant. So as you see, there are very different SLAs, real-time and offline. And by the way, if you have any questions, feel free to ask. Okay, the SLA is clear. Okay, now I'm going to show you the story and the process of what happened in LivePerson during the last couple of years, of how we moved our system. Let's start with the legacy data flow that we had. And actually, we still have, partially it's still the way it's running today. So we have real-time servers that work with the internet visitors, and the agents, our customers, are interfacing with some real-time servers that run in LivePerson. We have our farms, very big, many real-time servers. And they provide data. All this data is created as event files. And they have some structure, CSV structure, more or less. And they're sent to some ETL system. Again, this is our legacy. What does the ETL does? ETL does a lot of processing. It takes all the events and create a session from them, sessionizing. And modeling, it creates a model with some definition that was, and then create a schema view. There might be different schema views. And all this it's the ETL process. Once it's done, everything is written to Oracle, a BI data warehouse. That's the way it used to work for us for many years. But there are many problems in this situation. I can tell you the biggest problem is that this doesn't scale. When we want to grow bigger, Oracle cannot hold so much data for long periods, because if I want now 24 months to retain and to be able to query this data by customer, it's just impossible. And ETL cannot scale, because if I want to add more functionality, more change the events, there's a lot of coding that I need to do in the ETL. It doesn't scale. I mean, ETL can scale as I can add more workers to ETL, but if I want to change functionality, it just doesn't scale. And all this there's a lot of legacy here. And we started to think how we can get rid of this. And the conclusion was that we need to, and it's not one conclusion, but what happened is that we started to move and to replace the parts one part at a time, not everything together, but one at a time. So the first one to replace was the BI data warehouse. And we moved to Hadoop. So instead of a BI data warehouse, we now have one Hadoop with HDFS. The ETL write the data into HDFS. And then there is another BI data warehouse, which is these days is Vertica, which holds only part of the data. It doesn't need to store all the 24 or 18 months or whatever we want to store, because it cannot. It takes only a fraction of the data that is relevant to the report, only fraction of time, and only fraction of events that are important. If it's not important to the BI data warehouse, it's not there. Everything is in Hadoop. So everything is stored in Hadoop. This part was done more or less 2 years ago. And then we moved to the next step. And the next step was move to Kafka. And now we mentioned that ETL is a very complicated system. And instead of ETL, we just put Kafka. And this is magic, because Kafka actually does not do any processing, any coding. It's just a pipe. It's a buffer. The real-time servers write to Kafka, and the data is written to Hadoop. So where all this ETL coding and logic goes to, it actually was not necessary. Why? Because the events that come from the app server, the real-time servers, going straight to Hadoop, and then whatever I need to manage and to do the ETL, I can do here to the BI data warehouse. So there is a MapReduce here that transfer the data into the BI data warehouse, and actually I don't need to do anything in the middleware there. And then, yes?
What about sessionizing?
So the question was, what about the sessionizing? It's very interesting, because actually we don't need sessionizing. Because sessionizing you can do here for specific, if you really need the sessionizing, the question is what is sessionizing and why you need it. And there was a lot of discussion about sessionizing here. I will not go into this, maybe we can take it offline, but I can tell you that in fact, there's no sessionizing here, and if there is any need for sessionizing, it will be done here at this point. Okay? Yeah. The next phase, new producers. So once we have Kafka, which is a very thin layer that just do buffering, it's not ETL. As I said, ETL is a system that could not scale. Now I want to have new producers, more real-time servers with new protocols. It's very easy. You just define another topic in Kafka, and we did that. We created new real-time servers with different protocols, and they use the same Kafka. No need to change anything in ETL, because Kafka has no code in it. It's just a buffer. Next, real-time BI. We want real-time BI. So we have all the data is streaming. We have Kafka. Let's introduce Storm into the system, and we did that. Storm, for anybody that doesn't know, Storm is a real-time streaming data container, and the data is streaming from the Kafka into Storm. Storm does the processing and provide the data to any other consumer that needs it. In that case, it will send it to some BI dashboards.
Can I ask another?
Yes, sure.
Where does the Storm store the data? Or the dashboard?
Okay, so there was a question, where does Storm store the data? This is not mentioned in this slide, but in fact, Storm, what we do is that Storm aggregates the data and writes it into some metadata, in our case, Couchbase or Cassandra, and then the dashboards will read the data from there. But you're right, Storm by itself needs somewhere to write the data. So we have some real-time analytics databases. We have two cases, Cassandra and Couchbase. We will use both of them. Probably eventually we go with one of them, but currently we use both of them. And they are the real-time analytics database. So they store a real-time data, and so you can query them and see exactly what happens now, because Storm does it very immediately. Okay? And now the next phase, okay, so everything is working, but we wanted also to standardize our data model. And this was very important to us because every change in data model, the issue that we had with ETL, every change in the data model, we need to go and change code in many, many places. But if we define a structure, a schema, then everything should adhere to this schema. And we used Avro. And so the new real-time server writes data using Avro, and I'll go to explain what Avro does. And then the Avro from Kafka is written as is to Hadoop using another process that from LinkedIn. It's called Camus or Camus in French. You may notice that the old real-time servers do not write Avro. We didn't touch them. They just write to Kafka. The data is collected, and the BI dashboard uses this data. And new real-time server, we started to use Avro. We didn't want to change the legacy code. But as Kafka allows us to anything that is written can be used. It doesn't enforce any model, any schema, anything. By the way, I did not mention, I think in the beginning, Kafka is an open source that was contributed by LinkedIn. Storm is an open source contributed by Twitter. And Hadoop is just Apache project. Okay? But Kafka is also an Apache project today. And Storm is going to be also Apache project. So, yes?
Sorry, too many questions. You can stop.
Yeah, go ahead.
It's about the level of the data in Hadoop itself. Do you use any kind of metadata layer such as Hive or HCapital for the data?
So the question was whether we use any metadata infrastructures for the data stored in HDFS. So currently we store the data as is. I will go a little bit to explain what we do with the data, but Hive, you can run Hive over the HDFS data without any problem.
But does Camus handle the Hive partitions and everything?
No. Camus doesn't handle anything. You just write the data to the folders, to the partitions, and then you need to partition them for Hive if you want. We have some issues with Hive. I'll go to this later when I'll talk about Avro. Remember to ask me when we talk about Avro, we have some problem with Hive. But basically, it's pure HDFS. We don't use any HBase, anything else. And Hive, just you can query over HDFS. Okay? Okay, and the last thing was to define what is our single source of truth. As I said, one of the big challenges was that we had many different systems, and each one was its own single source of truth. And when there was one report and another report, and the data was not the same, there was a question who is right and who is wrong, and where is the bug, in this one or that one. So now we have one single source of truth. Can you think where in this area it will be the single source of truth?
HDFS.
Right, HDFS. So the data that arrived here is a single source of truth. Note that this data is the very simple raw data that was coming from the real-time servers. It was not changed at all anywhere, so it's really the single source of truth. There was no ETL process that changed it. From here, it may pass some MapReduce that will change it and will aggregate data, will collect data, whatever. But whenever there's conflict, you can go back to the single source of truth and run this process again to make sure that you have the correct data. By the way, Hadoop holds immutable files, so once it's written, it's there, it's final, you cannot change it. You can delete it, but a file that is written is not something that anybody can change. So it's really the single source of truth. Question?
One more question.
Yes.
About, you say that Hadoop is the single source of truth, but there is a lag between the time a single data entry goes from the real-time servers to Hadoop. How do you handle problems that happen along the way? Eventually they will arrive to Hadoop, but how do you know how to handle that?
So what you
mentioned duplications because of
what you say? What's your name?
Ariel.
Ariel. So
Ariel.
Ariel. So what Ariel says is that there is that it takes time for the data to arrive from the real-time servers to Hadoop, and if the Hadoop is the single source of truth, and the data arrives in latency, how can it be the real single source of truth? So my answer to you is if we define that this is the single source of truth, only what's here is the truth. And if the truth did not arrive there, you still don't have the truth. So if the event happened there and it still did not arrive, once it arrived, you'll have the truth here. Until you get it, you don't have the evidence for the truth. Okay?
It does mean that you can have data in Vertica, which was the truth like for an hour ago, but now you have additional data inside Hadoop, and this is not the same data.
No, the data was streaming, arrived to Hadoop, from Hadoop was uploaded to Vertica. Now more data was arrived, more data uploaded to Vertica. Vertica takes only from here. It doesn't care that it was half an hour earlier there.
So the calculation to Vertica, the second one will only take the deltas, the late data, not the entire data.
So Vertica only takes deltas from here, and it introduces some issues for the calculations, like how do you do sessionizing and all the questions that you raised. And you're right, there are challenges about this. It was much easier if you could write everything to Oracle and get everything done in Oracle, but it just, as I said, it doesn't scale. That's why we need Hadoop, okay? Yes?
How can you avoid from situation which data arrive to Storm, but not to Hadoop? In which way?
Okay, so your question was how can I avoid data getting to Storm and not to Hadoop? I will get to this when I talk about our resilience solutions, but you're right, there is a problem here, and you can see it. The same data arrives twice, once to Storm, one to Hadoop. As I said, this is our single source of truth, so whatever comes to Storm is not the single source of truth. It's important to understand. We'll talk about this later. It's a data that is shown to real-time users, but it's not the single source of truth. If it's wrong, you need to go here to check it, to check the real story, okay? But not in real time. I'll get there and explain how we do this, okay? It's really a big challenge that we have. And we found a solution for that, and I will share it with you, but just wait a little, okay? Okay, so now I'll start to dig a little bit into Kafka and all the problems that we have, all the issues and the challenges. So why Kafka is our backbone for data, and what are the features that Kafka provides? So it's a central message bus, as you saw. Everything is going to Kafka. It can support multiple topics, as we saw before. We can have different real-time servers that will use different topics, and we can refer to them differently. They can provide different SLAs, as we will see. It's a write-ahead logger, actually, Kafka. So everything is written to a file very, very quickly. Kafka is very quick. It's distributed, and it's highly available. So if one server fails, the rest of the system will continue working. Eventually, you need the events coming from that server that fails, but the system will not stop working. There's horizontal scale, so if you need more processing power, you can add more servers, and you enlarge your cluster, and you can very easily have more data flowing. And what the numbers that LinkedIn provide are tens of megabytes per second per node. So if you want 100 megabytes per second, you just need to have 10 machines.
Producer or for consumer?
That's for producers. Consumer are about tenth. I think if it's 10, it will be megabyte. If it's 10 megabytes, the consumer will be megabytes. But again, you can play with this. That's their numbers. Of course, it depends very much about the implication. The service, and this is very important with Kafka, because in the beginning we thought about using JMS and message queues and whatever. And what's so good about Kafka is that it's agnostic about the consumer's state. It doesn't care what the consumers of the data did with the data. Did they take the data? Did they not take the data? It doesn't care. It just provides them a service, take the data, and do with it whatever you want. I'll go into the details to explain how they do it. But by doing that, they took off from their responsibility, Kafka server took off from its responsibility the need to deal with which are my consumers and what have they done. And that's why it's very easy to scale it, because a system like JMS that needs to manage all the consumers, very difficult to scale horizontally. And Kafka has a retention policies because it's a file, it's just a rolling file. And you can define, I want to retain data in Kafka for 1 day, 2 days, 10 days, and the rolling file will keep everything for at least 10 days. And you can define the file size. I want 10 gigabyte file size, so the Kafka will retain at most 10 gigabyte file size. And all these things are the reasons why we chose Kafka. There are issues with Kafka, but these are the benefits that we gain. This is a diagram taken from LinkedIn papers. What you can see that there are many producers on the green ones, and many producers, and there's one Kafka. So all the producers will send data, all the consumers read data, and everything is centralized in one data bus. And now I want to explain a little bit about how Kafka works. So the pipe here in the middle, this is Kafka. That we have 3 nodes of Kafka, and every node that starts up a service registers itself into Zookeeper. Zookeeper is another Apache open source to manage real-time services. It's kind of service directory, and there is an API that of Zookeeper that a service can register itself once it turns on and unregister once it turned off, and then anyone can ask Zookeeper which are the servers that are running. Now we have producers of Kafka messages and consumers. We have many. A producer, according to the producer API, in order to send a message, first need to go to the Zookeeper and to ask which are my brokers or my nodes to which I can send the message. And it gets a list, and then using this list, it sends its message to one broker. And the decision, the way the API does it is some kind of round robin, some kind of round robin, so it's balanced. Now the 2 other producers will just do the same. We'll go to Zookeeper, and each one will send to a different node, or maybe to the same node, according to the way the API decide to which to send. Yes?
You have to query Zookeeper every time you want to send that?
You don't query every time. I'm not sure. No, I think it's cached. Yeah. If you lose your connection, then you need to reread again. But basically, it's cached. And now, what do the consumer do? Again, they go to Zookeeper and ask where are my nodes, and then it goes to the nodes and start to read data from them. And all the consumer will read from all the nodes. That's the way the very simple API works. Now, you have 2 ways that consumers can work. Consumer 1 that we see at the bottom reads the data from 2 nodes of Kafka. The topic that it reads resides on these 2 nodes, and it just reads the 2 of them. Once from here, and just it reads according to where the data is. The two other consumer 2 and consumer 3, are called a group, consumer group. When you use a consumer group, you actually use this to load balance the consumer throughput. So you want, now I see that one consumer cannot read all the data in a timely manner, so I create a group, and the work will be divided between the groups. So if consumer 2 read the bulk of events, consumer 3 will not read those events, will read the next event. So they work together as one group of consumers that read only all the data only once. Okay, clear? That's very good if you have a lot of data and want to manage the way you read it in many consumers that will share between them. Just use this, and this is very easily provided by Kafka API. Now, Kafka holds, as I said, the messages of Kafka are stored in files, and each file has, or each topic is its own files or file sets. So, and for each topic, you can define, you know that there is the first message, or the minimum offset of the messages, and the maximum offset of the message. So where the first message is and where the last message is. And of course, this changes all the time because events are being written and the max offset is changing all the time. And once Kafka do retention management and delete file, then a whole set of events is being deleted. But they all the time manage this min and max offset. Now, when you read data from Kafka, you have the common way, which is use Zookeeper. I didn't mention it before, but the API store use the consumer API. I'll go to this. Store the offset, the last offset that I read, store in Zookeeper. So next time I come to read the message, the API goes to Zookeeper, retrieves the offset, and go through this offset and read the next messages. There is a possibility to read earliest offset, to start from the beginning, and to read from the last offset, start from the last event. And this is very useful because many times you want to see all the events from the beginning, from the last three days for some reason. And sometimes, like the native console that Kafka provide, there is a Kafka consumer console that they provide that always starts with -1. So once you run it, it will go to a topic and show you the events from now on. As you'll see events streaming as they see, but you don't need to see all the history that was stored. One thing to mention here, I think it's very important for anyone that starts with Kafka and anyone that starts with Kafka fail on this. If I have an application that reads from Kafka, and then for 2-3 days I didn't run it, and then I start to run it again, suddenly I may get an exception. What's the exception name? Out of offset, out of range. Offset out of range exception. What is offset out of range? It means that the offset that I kept in Zookeeper is not there anymore because the retention management deleted this file. So now the Kafka API doesn't know where to read from now. The offset points to some place that does not exist anymore. Where can I read? So if you're running your consumer all the time, it will never happen. But if there was a downtime of the system for over the period of the retention, then you get this offset out of range. And then what you need to do, you need to rerun the application with either -2, which will bring everything from the beginning, but then you know you lost some events. Or you say, I don't care, I lost events, I will lose everything and read from -1, and we'll just start from the end of the topic. Yes?
Have you given any thought to storing offsets in the middle of the string? So, I don't know, for example, I have a process that reads a batch of messages and it fails, and I want to just reread that batch.
So you're asking about how to reread batches from a certain point.
Yeah. I mean, do you save offsets as you go?
No, so we don't save offsets. Kafka does it for us. Not only Kafka, I will explain a little better, but we don't manage. One drawback of Kafka is that, and I'll mention this, You cannot go to a certain point in time and invent, say, I want to read now from here. It's very difficult to know where it is.
You have to save the offset in advance, no?
If you want to save a certain point, you need to save this offset, but nobody does this because, remember, Kafka is something for doing a very high throughput of data that is streaming all the time. You don't start to save offsets for certain points in time. It doesn't make sense. You don't do this. Kafka is not for that, okay? But it's true that if you want to go to a certain point of time, it's very difficult. Camus does this, but it again, yeah, it stores the last thing that you'd read, but you cannot go now to the second of the time, to the time of the year this, and bring me the data from there.
I mean, the scenario I'm talking about is, say, Kami reads data and pushes it into HDFS, and suppose there's a failure, and it's just a failure, you know, the process that
So it doesn't commit the offsets, and the next time it runs from the latest.
the
offsets.
previous. Okay,
Yeah.
so it reads first and then does
Yeah,
something and commits my
This
next
is the
offset.
resilience.
Yeah, I'll go to this in a minute, okay? Just, I think the next slide talks about this. So yeah, this is exactly the next slide. So we have, these are the Kafka APIs, very simple APIs. Not so simple, but the concept is simple. One API is for producer and one API is for consumer. Producers, there's only one API and is very simple. And as you saw before, when you write, you need to provide Zookeeper URL. The API goes to Zookeeper, retrieves the brokers, the Kafka brokers, and send the message to one of them. That's the API.
And the integration with Zookeeper is an integral part of Kafka? Or
Right.
yeah.
You need Zookeeper to work with Kafka. You cannot work with Kafka without Zookeeper. Yeah, it's part of working with Kafka requires Zookeeper. I mean, not exactly. Not exactly. You could. There is a mode that I think in Kafka 07 they had a mode that you could work in one node of Kafka without any Zookeeper, and then the producer wrote directly to the node, and the consumer read directly from the node. But in Kafka 08, this doesn't work anymore.
You cannot choose an LDAP or something else.
No. Only Zookeeper. Yes. Zookeeper is a cluster of very much like Kafka. It's a cluster that can grow scale horizontally, and in our case we have 3 servers that each one. It's actually all the data is replicated between the 3 of them, but you can have more servers. So yeah, Zookeeper is essential part of the system, and it is critical that it will be available. So it's also highly available. Yeah. So about the consumer API, we have what's called the high-level API. What's the high-level API? If you you install Kafka and you run the Kafka console consumer shell script, it uses a high-level API, goes to Zookeeper, retrieves a list of brokers, Kafka brokers, and read from them. But in our case, in all the uses that we do in our implementations, we don't use the high-level API, and I'll explain why. So Kafka provides also a simple consumer API, in which you go directly to where you want to read the data, the broker that you want to read the data from, and read exactly. You provide the offset, and you can read directly from that broker. Why is it needed? So in our case, Kafka Spout. This is in Storm. In Storm, we must use this, and I'll explain why. Kami also use this term this way. Again, I'll explain why. And Kafka Hadoop Consumer, it's another way that we read data from Kafka to Hadoop. Why they use the simple consumer? Maybe you can think, you can suggest why we cannot use this high-level API that updates Zookeeper directly. You have any idea why we need to read ourselves and not let Kafka do all this Zookeeper management for us?
The offset management?
The offset management, yes. Okay, so I'll help you with this. The reason is that Storm is a very good example. Storm reads data from Kafka and start to process this data. If Storm used the high-level API, then once it read the data, it would commit to Zookeeper exactly the offset that it read. But then it starts to process, and then suddenly something fails. Then how Storm can decide to roll back and to read again the events that could not process. So what Storm does, and I'm going a little to the way Storm works, Storm get events from Kafka, start to process them, and once it get acknowledged that everything was okay, only then it commits to Kafka. And for this reason, Storm manage itself the way, it doesn't commit to Kafka, it commits to Zookeeper. Storm manage itself. So Storm manage itself the way it commits the offsets into Zookeeper and cannot count on the high-level API. Exactly the same with Camus. Camus read the data and start to process it, and until it finishes the processing, it does not want to commit to Zookeeper that the data was read, because if it fails, it needs to read again the same data. So it needs to have the offset stored in a place when Camus can go back and reread data that was already read.
So what is the difference between that and the high-level API?
So,
Don't you need to commit with the high-level?
so the high-level API, once you read the data, the API itself committed to Zookeeper that you read this data. Because it said if you read the data, you read the bulk of, let's say you read the bulk of 1,000 messages, and the API committed to Zookeeper that now this consumer moved to this new offset. But then you cannot roll back because the API hides from you the way it manages the commitment into Zookeeper, okay? Yes?
Do you have a penalty, performance penalty with the so-called simple consumer there? Because I was wondering, since you have to go back in time and the message size may vary, and Kafka actually needs to calculate where in the disk or wherever in the file it saves the message it needs to get the data from.
So,
If it tends to read all the messages before, which we do it like this.
okay, so the question was if there is some penalty of performance that we use in the low-level API, and I don't think so, because what the high-level API actually does is provide for you some way that you don't need to deal with managing the offset. But if you write this code yourself, you just do the same. It's not that you will use more CPU power instead of the API. The API just, it's a code that after you read the data goes commit into Zookeeper that this is the offset. And you can use this yourself, but don't do it once you read the data, but only once you completed your transaction. I don't think that there is any penalty of performance here.
The high-level API use the simple consumer itself.
Right.
The
High-level consumer actually wraps the low-level consumer.
So there is some way that Kafka keeps where in the file is every message, so you can go back and forth. Okay.
Kafka doesn't, when you read, you know where is the last offset that you read, and you keep this for yourself. Kafka does not do anything for you. You, as a consumer, need to manage everything about the offsets. That's what I said in the beginning. The Kafka server is agnostic to its consumers, doesn't know what they're doing. Okay? Yes?
I'm curious how you manage the offsets when you use Kafka spouts, because usually when you have a Kafka spout, you have a couple of Kafka spouts working together. So every Kafka spout instance use a range of offsets and read it from there.
So you were asking about how Kafka Spout manage the offsets. And Kafka Spout is an open source that is part of the Storm contrib, and it's not our source. We use it. You can go to the code. And, it's as simple as you describe. I don't want to go too much into Storm at this point, but basically, it just do exactly what the high-level API does, but it only does this after it gets an acknowledgement. So it reads the data, stores it in some buffer, waits until there is an acknowledgement. Once it gets an acknowledgement for this bulk of data, each bulk is managed inside Storm. Once you get this, it can go and update into Zookeeper that this bulk was committed. And until then, it will not read more data from this topic. Okay? But I really don't want to go now into Storm. This is another discussion, but basically what Storm does is very simple. Kafka Spout, read a topic, process it, acknowledge, then read again, process, acknowledge. And if you do it in parallel,
There is a task for each broker or partition.
yeah.
You don't read the same partition for 7 tasks.
So only one task.
Yeah.
Each partition for each broker. So
Yes.
you have 5 servers, 5 partitions, you have 25 tasks.
Right. So each partition will be, and that's the way it scales. And it's about the same way with Camus. Camus create a mapper for each partition, and this mapper works standalone with this partition. It reads and acknowledge once it completed writing, passing it by. But all the mapper eventually collect all the data and pass it to the MapReduce workflow. Okay. So just to again, there is the high-level consumer API, but in all our system we actually don't use it. We use code, and by the way, the code that it's open. These consumers that wrap the simple consumers, they're all are open source public domain. Kafka Spout is, as I say, is part of the Storm contribs, and you can find it in GitHub. Camus is part of LinkedIn open source that they provided, and we use it. Kafka Hadoop Consumer is another open source of the Kafka project, and all this is not. We didn't write much code here. Yes.
You said you mentioned Camus and the Kafka Hadoop Consumer. Did you use both of them, or did you just start with some?
We use both Camus and Kafka Hadoop Consumer. I don't want to go into details why, but basically I'll tell you why. The Kafka Hadoop Consumer that is part of the Kafka project is very good to read streams of strings, and Camus is very good to read Avro data. And when I go to Avro, I'll explain about Avro. I'll explain why Camus was basically started with Avro because that's the way LinkedIn worked. They still work today. Kafka Hadoop Consumer was not sufficient for the Avro. And since we started with Hadoop and Kafka and only then moved to Avro, then we need to introduce Camus. So currently we have both of them. But I think eventually we will work only with one that aggregates everything. Okay, so here's the code example of how the API works. I don't think there's much need to explain this because you can find this in all Kafka resources in the internet. But there is a producer API and a consumer API, and the producer just define a list of messages and send them, and the consumer just define a message stream, and then traverse them and read in a for loop on the messages. That's a very simple API. As I said, all the consumer code that we use in our system is actually an open source that was written by other contributors. Most of the code, no, because we also have many tests that we wrote using this API, but the real thing that works in production is most of it is open source. Yeah, maybe I need to mention that we wrote many tests that use this API, and we have a lot of testing for all these frameworks, a lot of many unit tests and system tests, and yeah, a lot of code was written for testing all this, and load tests. Okay, until now I didn't speak about. Yeah, you had a question?
Unless we're going back to Kafka, I have a question about Kafka.
We'll go to Kafka. Yeah, we are in Kafka. We didn't leave Kafka yet, but I want to introduce what Avro is doing. So Avro is actually as it says, a schema representation using JSON. So we chose Avro as the way to manage the schema of the messages that are being passed to Kafka and through Kafka. It provides a schema representation, and also it's the data serializing system. So it's both the schema representation and the serialization mechanism. It provides primitive, there are many types that it supports, primitive, like Boolean, integer, long, string, etc. And complex types like record, enum, union, arrays, maps, and fixed. I want to mention one thing, the word union here. This union, when you say union type, I don't know if everybody here, for C, programmers that wrote C, in C there is something called union, which is, you can define object and another object that overlap the same data block can be represented in different object representation. This is what's called enum. Union, sorry. Union in C, it's union type. Avro is very strong with union, and for us it was very good because we, for example, created an event. This event had a common header, but the body of the event changed between the different events. So each event had different body, and then with the union you can just replace different representation, and it's totally different. They don't share any fields. There's a big issue with union today, and the issue is that with MapReduce everything works okay. You can write the data and read the data to Hadoop, but if you try to use Hive, just a minute, I just want to mention that the Avro is very common in the Hadoop world, because Hadoop, Avro files include file header in Hadoop. There is a special file called Avro file, which stores the schema of the file in the file itself. So once you read the file, you first read the schema, and through the API of Hadoop, you can find the schema of this file, and with this schema you can read all the records. And then if there are many schemas revisions, each file, you know exactly which is the revision that it holds because it's part of the file. This is something very strong in the Hadoop world. But as I said, if you created object with union inside your object, inside your data files, you will not be able to read this data with Hive. And that's a big limitation, and for us it's really a big question, do we want to work with unions at all or not? Because not Hive and not any other, not Pig and not Impala and not any other way that allows you to read data in some SQL format or some easy way to read the data and traverse inside it does not support union. Yes?
Does it also, problem you're describing, is it also referring to unions which of null and regular values?
No. If you have only one union type and null, this is supported. But if you have two or more different types in the union, it just will not work.
So if I understand correctly, between the lines, what you said before, the schema version is embedded in each record in the header probably, and you're using unions for that, like for embedding multiple records on the same record?
Event type. We just use event type and then use the union that holds this thing.
So the actual data is actually a union of multiple data types.
Yes. So as I said, we moved to transfer everything new that we write today should go through the Avro schemas, and we have schemas that evolve a lot and they change all the time, and people are writing new events and change the event, and this is a very, very good way to enforce the way we manage our data. Before that, in our legacy systems, we had some Word document that everything is written there, and everyone that needs to do the change needs to go to this Word document and make sure that everybody is aware of that. And now with schema enforcement, life is much easier because it just does not allow things to change without breaking them. But now that we read this event from Kafka, we must know with which version it was written because we need to be able to read it. So there is a possibility to write the whole schema inside with the event, but then you'll have very big, each event will have very big schema which is repeating itself, and very small event, and it's not, not efficient. So we provided some mechanism to overcome this problem. And I want to explain this. And this is very interesting. So the story goes like this. I have now an event, and I have now schema version 1.0. This is the version that currently I'm working as a producer. I create an event. So I create a message according to this schema. Now on the right top, I show you how I build the event, the message. So first of all, if this is the first time that I use this version of the schema, I want to register it to some schema repository. At the next time we'll try to get, or the next time that I'll try to create another message like this, I don't need to register it because it's already registered. So the first time a schema is being used by a producer, it's being registered. Now I add the revision of the schema 1.0 as a header to my message that I'm going to send to Kafka. Then I encode the message with the schema number 1.0, and I put the encoded message in the message, the encoded event in the Kafka message. So now I have a Kafka message, which have a header, which is the schema version, and the event itself, which is encoded with the same schema version. And now I can send this message to Kafka. And now here come the consumer. So the consumer read the message. It's a buffer of bytes of Kafka. And there is a common API here that extracts the header and obtains the schema version. And then it reads that it's 1.0 because it's in a certain position in the header that it first reads. This is our implementation. It's not part of any Kafka utility. It's our implementation. Then it goes to the schema repository and retrieves this schema from the repository. And as I say, the first time that this event with this schema was written, it was registered in the repository. So now it should be in the repository because somebody wrote it. I get the schema. I decode, the consumer decodes the message with this exact schema version. And then we have the correct message at hand, and we can send it, pass it by, and the same thing we do both in Camus and in Storm. This whole mechanism, is it clear or?
Do you have a separate message per event that goes to Kafka? And that's why you need to strip out the metadata outside, so it won't be.
We have one schema for all events in our case, okay?
If I say if there is 1 million events, will there be 1 million messages in Kafka?
Yes.
Also,
Each event is
so
a
if
message.
the messages, the events together in a single message, then you don't want the overhead of adding the schema to each.
Right. Each event is a message in Kafka that we send to Kafka. Yes.
Do you use generated Avro code, or do you use generated code?
We use Avro. Avro. When you use Avro schema, Avro generates the objects for you, and you use them in the API. That's the way you work with Avro. Maybe I didn't explain it. When you work with Avro, you define I didn't go into all the details of how Avro works, but because there was a question, I'll explain. You define a schema, and then and we do it in some Maven plugin that they provide. You create POJO objects from this schema, and with these POJO objects, you can store them. And we store them in one jar, and then you can use them either by the producer or by the consumer. Okay, but note that this is done by the producer, but the consumer, actually it's
Some consumers use the
Generated, other ones.
other will not. Why? Because if I here use a generated, I must have a specific version of the schema that is linked to my project.
If you work with multiple versions, then you don't generate.
Yeah, I don't want to go into all the details. There are some details here, but basically it's right. You may have the latest version here linked to your project, and then you have the generated POJOs, or you may have only the schema. You'll be able to deserialize using your schema alone, and then you don't need to link this with you. We use both systems. I don't want to go into all this. I mean, we can take it. It's a bit.
Just a last question.
Yes, sure.
Sorry. Do you so generated code? Do you use it as the domain object in the producer and the consumer, or is it do you have separate domain objects for the data?
That's the domain object.
Sorry,
That's the
domain
schema is the
object?
domain object.
Yeah,
The
the
actual
yeah.
code uses this as the single source of truth.
Yeah. You go into details of the way working with the Avro. I mean, we can well, let's because I don't want to go into the details of Avro. There's a lot of talk about Avro, and I didn't want to go too much, just to understand. Everything that you see here is not part of Kafka. LinkedIn are doing this, but they did not deliver this as an open source. How do I know that they're doing it? Because I looked at the code of Camus, and I saw that that's what they're doing. But we take all this ecosystem and we created an open source that we're very soon going to publish under LivePerson GitHub or wherever. And this ecosystem of manage the message revisioning, including the schema repository and the consumer and the producer wrapper API, is going to be part of the open source that we'll provide very soon. Okay, so that's I think good news. And once this is all done, I'll post it. It should be in a couple of weeks, and I'll post it in the meetup. A link to this I'll post in the meetup event. Okay. So this was about how we manage the revisions. The other problem that we have is the resiliency problem, and it was raised before. I think you raised it. So Kafka is a very high throughput and everything, but it's over the network, and and there might be some maintenance, some problems. How do you manage the resiliency of the system? And this was a big issue that we dealt with many times in discussions, and for a long time, it took us a long time until we came to some decisions. What we decided to do, as I showed you in the beginning of the lecture, we actually have two types of customers with two different SLAs. One is the real-time customer on the left, and one is the offline customer. And as you remember, the real-time customer wants the data fast, but it's okay to lose events if they didn't arrive on time, because I only show dashboards. It doesn't matter that the data is 100% accurate, because dashboard change all the time. Once I now see this, maybe I think it's not accurate, but a minute after I see something else, so I don't even know what I saw and how accurate it was. On the other end, the offline consumers need the data without any data loss, but it's okay to get later there. Okay? Okay, so what do we do? Our producer sends the data two places. Every message is sent twice. Once it is sent to a topic, a Kafka topic that we call the fast topic. And then again, it is sent to a local file and saved there. Why local file? Because this is the most robust place that I can count on, that I know can be the best place I can be sure that I will have access to. It's not networking. It's provided by the operation system. It should be the most robust place. After that, there is a process that we call Kafka Bridge that reads the local file and sends them to another topic that is called the consistent topic. So we have a fast topic that everything gets there very fast. And we have a consistent topic which everything gets there not so fast, but very consistent. And we have two types of consumers. One is Storm, reads the data from the fast topic, and one is Hadoop, Camus, that reads the consistent topic. Who of them is the single source of truth? Which one of them? Which one of them? The right. This is the single source of truth. This is not. This is not a single source. If there is an error here, you'll see it only in real time. That was a decision. That's the SLA. You might say, I don't like this, but this was our decision. We saw that we could not provide both very quick responses and very consistent, and with so big scale, we could not get everything together. So we decided to define different SLAs and provide different systems to different SLAs. Does this help you?
Now I have the question.
Okay.
Why not to use the mechanism of Storm and to store the data in HDFS in the last bolt of the Storm?
So Storm will pass the data. Yeah. So the suggestion here was, why not use Storm as the streaming process to write to Hadoop? And the answer is very simple. If we use Storm itself, may lose data. Storm itself has processing. Storm itself is a system that is much less consistent than a MapReduce. Because if I just read from here data and write it to HDFS, it's the quickest way I could make sure the data arrives. If I pass it through Storm, it goes through a system from bolts and spouts, and there may be failures, and then I introduce more risk to data getting there properly. And again, the big problem is not there. The big problem is the data that gets to this fast topic. What happens if the Kafka is down, or if there's no networking? What will you do? So and also Storm needs a lot of CPU power, and just take Storm as your pipe to pass data from Kafka into Hadoop does not make sense. It's much easier to do it in a batch than to do it in a real-time streaming. But it's a good question, and I think many people thought in the beginning that this is the proper way to do what you suggest. And when you start to think about this, you understand that actually you don't want to do this.
The only reason I ask it is because Hortonworks suggests to create a bolt that can write to Hadoop.
So you said that Hortonworks suggested a bolt that can write that to Hadoop, and of course, there are bolts that can write data to Hadoop and to Cassandra and to Couchbase and to SQL, MySQL. There's many bolts that do that, but we don't want such a bolt to be our pipe for the single source of truth. We use, by the way, we use in some Storm topologies, we use writing into Hadoop, and that's okay, but not for the main path of writing into Hadoop. Okay.
What's the typical latency between the producers and the consistent topic? Seconds, minutes?
Between the producer and the consumers?
No, and the consistent topic.
And the consistent?
Yeah.
Okay, so the way we did it is we tail over this file every 5 minutes. So we have a latency of 5 minutes. Yeah, but that's the way we defined it. We could do a tailing, immediate tailing. We didn't want to do that because it's not so important that the data will arrive so quickly. Because if you want the data quickly, go here.
It just limits the amount of data loss you'll have if you lose a producer. That's all. That's the trade-off.
Yeah.
Can't you run
Yes.
from the local file directly to Hadoop without the Kafka?
Yes, but we didn't want to do that. So the question was, can we write the data from the local file directly to Hadoop?
Why we need Kafka?
Why we need Kafka? And the answer is that Kafka is our message bus. The local file is something that is written and immediately need to get out there and go into Kafka. Kafka is the main message bus of the whole system. If you start, so we have hundreds of real-time servers. If we want to manage for all these hundreds of real-time servers a direct write from local Kafka into HDFS, we need to create some process that does this. And there are some processes that can do that, but it's another process to manage. And we preferred Kafka to be our central bus, data bus. That's the decision we made here. But your suggestion was raised here before. We thought about this as well.
So you break up, the Kafka bridge breaks up the local file again into the individual messages and then pushes it into the consistent Kafka?
So the question was here about how Kafka bridge works, and we wrote some implementation, very, very naive implementation that reads the files, just read them, and just send bulks of data, like every 1,000 messages go, or whatever, send, and until it finished reads the file and then go to the next file. It's some kind of telling.
Breaks it up into
Yeah, yes, yes.
I have another question about the topology, the network topology that this thing
Yes.
Lives on. I'm assuming this is multiple data centers, or it's all in one data
This is one data center, okay? But we have multiple data centers, so this is multiplied in different data centers. We do not manage multiple data centers in one central bus. We don't do that.
Sorry, do you have a data warehouse in each data center?
We have Kafka in each data center,
And one data warehouse?
And how is it?
and one Hadoop in each data center. We don't have so many data centers, but we have one Hadoop cluster and one Kafka cluster in each data center,
And the data warehouse would be on?
and also data warehouse.
So
Yeah, Vertica. Yeah, Vertica data warehouse is.
Kafka sends messages through from one data center to another, or this is all local to the same data center?
Okay, so the question was about the distribution between data centers. Kafka, first of all, Kafka does not send messages. Kafka is some, yeah, consumer can read data from data centers. In our implementation, everything that you see here is in one data center. We do not move data across data centers. We do this only in Hadoop. Once everything is down in Hadoop, then we use some Hadoop replications, DistTP and things like that, but we don't do anything inside the data flow. We don't do any transfer of data between data centers.
how do you get a consistent, complete view of the traffic in all data centers?
You're talking about how we manage, if there is a,
Someone wants to see a report of page views and they want to see the entire data set, real time, the entire.
In real time or offline?
No, even offline.
It's replicated.
so, okay, so,
It's replicated the results themselves or the replica.
so on the real time, if there are two data centers that the data is being spread between two data centers, the same, for example, the same account or site is being spread between two data centers, then on the Storm world, you can, as I said, the Storm only send eventually the data into Couchbase or Cassandra. Then Cassandra can be shared between data centers, and then when you read the data, you read it from Cassandra. When you show it to the GUI, you show it from Cassandra, and then Cassandra can work onto that. But so you do it only on that level. And the same thing with Hadoop. Hadoop is synchronized. Once the data arrive down to Hadoop, it's synchronized between the data centers. But all this process is in single data center.
Regular Hadoop distribution or is it Mapr or something?
It's we do with DistTP. Yes.
So it does incur another leg of latency on the reporting, right?
Yeah. So this Hadoop DistTP add another latency, but that's okay. I mean, that's part of the game here. What's in Hadoop is late. Consistent, but late. As I said, I go back to the SLA. I said 4 hours. So within 4 hours, I have the data there. Okay? That's what we committed to. Okay, so this was the resiliency API, the resiliency. I want now, we're going to the end of the lecture, I want to mention some of the challenges that we have with Kafka. You should be aware of. So Kafka is an open source, it's quite new, and there's not enough supporting tools, in my opinion, like if you used to work with Oracle, or MySQL even. Kafka lack many of these supporting tools, no good viewers of the data, no good ways to maintain. They improve in 0.8, they improved much over 0.7, but still maintenance is not easy. There's no auditing mechanism. LinkedIn wrote some auditing mechanism, but they didn't publish it as a public open source. So currently they're the only one that can use it. We in LivePerson start to write our own auditing system for Kafka. So actually the auditing means that I want to know all the messages that were sent into Kafka and were read from Kafka, that I didn't lose any messages. That's from our point of view auditing, and this does not exist. So you need to count on the fact that messages were sent and were received, but you need to write yourself the way to make sure that it really happened. Again, as I said, we worked on this ourselves, did not complete yet. I believe that LinkedIn will publish this eventually as an open source, but I yet didn't hear that they're going to do that. It's going to happen. So Kafka does not guarantee that there are no duplications of data, and this can happen because some machine failed and was restarted, and data was not written. I mean, the producer thought that it didn't write to a machine, but it actually did write, and then it wrote to another machine, and then an event can be duplicated. That can happen. It's very rarely. So Kafka guarantee at least one semantic, what they call, at least one message guarantee. So each message is guaranteed to be at least once sent, but it might be more than once. Very rare occasions, but it can happen. So we need to be aware of that. And Kafka API is not I think it's not documented well enough, and that's sometimes it's difficult. It's an open source, so there's no support. Support is only in the community. It's good. There's a lot of stuff going there, but you cannot buy any support. It's difficult to replay messages from a certain. I think this was raised before. If I want to go now to a certain time of the day and to start from there, it's very difficult to do that. It's possible, but you need to write your own mechanism of how to do this. Not easy. So it's more to have your data flowing. As I say, you need to think of it as a buffer of data flowing, and you don't know exactly what's going on there. It's just flowing, and you cannot go back. You can go back, but you can go, I want to go now to this point. You will go somewhere. It's eventually consistent. Eventually consistent is general problem of clusters. It's a eventual consistency is a big known issue of distributed systems. We need to learn how to live with this. What's the problem of eventually consistency? There's no guarantee of the delivery order. If there was a session with 100 events, the consumer that gets this session may get them in different order than they were created, because they were sent to different brokers of Kafka and then were read in a different order, and this happens all the time. It's hard, but you need to be aware of that, and people that the order is very important, the consumer that the order is important for them, need to reorder them. So you cannot tell where is your message. The message was sent by the Kafka API. It's in some broker. You don't know. Do you care where your message is? Maybe you don't care. But if you did care, you cannot know where it is. So you need to be aware of that. It's kind of you cannot find your data on the Kafka brokers. It's not a way that you can go there and search for your data there. As I said, there's no guarantee for no duplications. There might be duplications, very rarely, but they might be. But eventually everything, I mean, it's eventually consistent. Eventually everything will arrive. So event is generated, it goes somewhere in the desert, and eventually it gets to its destination. When and in which order and how is, I mean, very fast, but exactly how many milliseconds or in the order, you don't know. Yes? Okay. So some improvements in Kafka 0.8 that were introduced. I don't want to go over all the improvements, but only 3 points that are important for me to mention. The first one is that partitions are now replicated. If before that the partition was damaged, you lost the data there. Now in 0.8 there is a way to replicate the data, and if you lost the data, you can find it in another partition. Replication is very important. Message send guarantee. Until now, they supposed to have a message send guarantee, but it didn't work. So when you send and you ask for acknowledge that the message was sent, you actually did not. You couldn't count on this. It didn't work. In Kafka 0.8, there is an API that you can send, and and get an acknowledge that the send was successful. And they changed the way the offsets are managed or counted. They moved from just a byte counter to row counters. And because of this change is much easier, much more friendly, because I see now I'm at line 1,000, line 2,000, and not just number of bytes. It's much more user-friendly when you read the offsets, but it's not compatible to the earliest versions. So when you move from Kafka 07 to Kafka 08, you actually lose all the offsets that you had, because you cannot change, you cannot move between them. So migration from 07 to 08 is, you might lose data or duplicate data, whatever. But once we move to 08, I think it will be, and we, by the way, did not move to 08 yet, because we started with 07, it takes time, but we intend to move quickly. I just want to complete this lecture by going back to the first slide and where our data world challenges and how we address them with all the technologies. So the first one was high throughput, if you remember from the first slide. And we have Kafka and Hadoop that provides very high throughput as systems. The other challenge was horizontal scale to address growth. And Kafka, Storm, and Hadoop, the three of them supports horizontal scale, horizontal growth and scale. And the next one was high availability. And if you remember, when I showed these challenges in the beginning, they seems to be very challenging. But as I said, in fact, we addressed them more or less, most of them quite well. So high availability of data services. So Kafka, Storm, and Zookeeper, all of them are highly available services. No data loss. So first of all is high availability. Because it's highly available, you don't lose data, because if a server fails, other server will continue work. I mentioned another point here, no ETL. ETL by itself is not a reason to lose data, but because there's so much code in the ETL and so much processing, there's many cases that I know that we just don't know what to do with some event because it doesn't go to anything. Something is damaged about it, or we don't know what to do with it, or because of a bug, and we just lose this data. We don't know what to do with this, and we just throw it away. So we lose data. And this happens a lot when you use a code that do the processing of the data before you move it to the Hadoop. And now that we don't have ETL, actually all this kind of data loss is gone. Real-time demands, Storm addresses the real-time demands. Enforce structural data with schemas. This is Avro, as I explained. Process big data and enterprise data to support all the reporting platform and all that. Kafka and Hadoop provides the means to help us address all the demands from the enterprise. Single source of truth, it's Hadoop. And again, no ETL. Using ETL could not, when you use ETL, you could not have a single source of truth because the data that ETL processed is no longer the single source of truth. It already changed. It's not the source anymore. But now we pass the data directly to HDFS as it was generated. It's a single source of truth. These are some reference to all the topics that I mentioned, and that's it. Thank you. I think.
To publish